Hello everyone, today we're looking at section 7.2, which is the dot product. So far with vectors, we have looked at adding and subtracting vectors and multiplying a vector by a scalar. Now in today's lesson and tomorrow's lesson, we are going to look at multiplying vectors. Okay, so today is the dot product. So the dot product is defined as a work, which is force times displacement, okay, where force is in the direction of the displacement. So if we look at the diagram here, notice that the two vectors are tail to tail, okay, and the angle is between them. So the work done is the force in the direction of the displacement, okay, which is from this point to this point right here, which using SOHCAHTOA is F times cos theta. So that's the direction of, that's the magnitude of the force in the direction of the displacement times the displacement. Okay, and just writing it differently, work is equal to the magnitude of force times the magnitude of displacement times cos theta. Okay, and this is for geometric vectors. Okay, just a couple notes here. The angle must be between 0 and 180 degrees. And also, if theta is greater than 90 degrees, that means that the work is negative. Okay, so example here, determine the work done. So we have a 50 Newton force acts 20 degrees from the displacement, and you're displacing an object 10 meters. So the work is equal to 50 times 10 times cos 20, which is 469.8 joules. All right. So, how would we compute work done if the vectors were given in Cartesian form? So how about algebraic vectors? Okay, so let's go through and do sort of like a proof here. So I have a diagram here. We have vectors A and B and the angle between them, right? And then I have drawn vector C. So if we look here, we have that vector B plus C is equal to A. Or rearranging it, we have C is equal to A minus B. All right, now we're going to use the cosine law. The cosine law says that the magnitude of C squared equals the magnitude of A squared plus the magnitude of B squared minus 2 times the magnitude of A, magnitude of B times cos theta. Now, if we notice, the magnitude of A times the magnitude of B times cos theta, that is work. Okay, so we want to isolate this in order to get an expression for work. So I'm going to bring the minus 2ab cos theta to the other side of the equation and bring the c squared to the right side. So we get 2ab cos theta is equal to a squared plus b squared minus c squared. And then we're just going to divide by 2 in order to get work. Okay, and there's our formula so far. So the problem with this formula here is that in a question, we're just given two vectors, A and B, not vector C. So we have to manipulate C. All right, so recall, so the magnitude of a vector is equal to the square root of its component squared, and this is just the Pythagorean theorem. Okay, so we have that vector A is equal to A1, A2, and vector B is equal to B1, B2. So vector C, okay, as we have above here, is equal to A minus B. Now recall to subtract vectors, you just subtract their x coordinates and subtract their y coordinates. So C is equal to A1 minus B1, comma, A2 minus B2. So the magnitude of C squared, which is what we need, is equal to A1 minus B1 squared plus A2 minus B2 squared. Notice I didn't square root it because the C is squared. Okay, and then I'm just going to expand this out using distributive properties. We have A1 minus B1 times A1 minus B1, which gives us this, and A2 minus B2 times A2 minus B2, which gives us this right here. Okay, so now we are going to replace our magnitude of A squared, magnitude of B squared, and magnitude of C squared in terms of their actual components. And what we get is A1 squared plus A2 squared. Okay, this is the magnitude of A squared. B1 squared, B2 squared, that's the magnitude of B squared. And then minus C squared, which is minus all this, so all the signs change. And we get this right here. Okay, and now if we look up at this line here, we can cross out a bunch of things, and it all reduces to this, which is 2 times A1 B1 plus 2 times A2 B2 divided by 2. And then the 2's divide out, and we get that the magnitude of A times the magnitude of B cos theta is simply equal to A1 times B1 plus A2 times B2. Right, and that is the dot product for Cartesian vectors. Okay, and notice that the result is a scalar, not a vector. Okay, and this is used to compute work given Cartesian vectors, and it's also used to determine the angles between vectors. Right, so if A and B are perpendicular, what must the dot product equal? Well, if we are, I'm just going to wait for this to load here. Okay, so if we're exerting a force this way and the displacement is this way, the angle between them is 90 degrees, there is no work done, right? And the way that we know that is mathematically is that A times B times cos 90 degrees, cos 90 is 0. So that's just equal to 0. All right. So, example, determine the dot product of these two vectors. So the dot product is simply you multiply the x coordinates plus you multiply the y coordinates together, and we get 8 plus negative 21, which equals negative 13. Okay, next example. Determine k so that the vectors are perpendicular. Okay, so again, perpendicular means 90 degrees. So when we do the dot product, it must equal 0. So we get 2k minus 20 is equal to 0. 2k equals 20, which means k must be equal to 10. Right. Now just a couple properties here. A dot B equals B dot A. Okay, you can switch the order. It doesn't matter. You get the same result. And A dot the sum of two vectors B plus C is equal to A dot B plus A dot C. All right. So next example here, is the triangle A, B, and C a right angle triangle? Okay, so the note I have here is don't compute the dot product of the given points because they are not vectors, right? So what we have to do is we actually have to create vectors, right? So the three vectors are, we have AB, that's a vector, we have AC, that's a vector, and we have BC, that's a vector. So remember what AB is, that's the coordinates of B minus the coordinates of A. That's equal to 1, 5 minus negative 2, 3, which equals, now that we subtract them, we put our square bracket in. So 1 minus negative 2 is 3, and 5 minus 3 is 2. Okay, AC is vector point C minus point A, which is equal to 3, 2 minus negative 2, 3. And that is equal to 5 and negative 1. And finally, BC is C minus B, which is 3, 2 minus 1, 5, which is equal to 2, negative 3. Okay, now we have the vectors. Now we want to see if the dot product between any pair is equal to 0. So right away I would look and I'd say, okay, well we have 3, 2, 2, negative 3. Those look like negative reciprocals. Let's test those out. So we do vector AB dot BC, and we see that it is in fact 0. So since the dot product of one pair of vectors is 0, it must be a right angled triangle. And there is your work for today.